So this technique is partial fractions. And basically what it is the backwards of our algebraic fractions. So normally we would have several fractions added together. We'd combine them all into one complete fraction. Well, partial fractions sends it back the other way. You got an algebraic fraction, one complete one, and we want to break it up into bits. So if you had to find the integral of some polynomial on polynomial, well, the first thing we still do is a polynomial division. So we look at the degree and see if we can do that. Now once we've done that, on the bit that is not now just a nice algebraic statement, the bit that's got the remainder over the divisor, if you like, that we want to factorise px. Now when we factorise that denominator, remember all polynomials can become linear factors or quadratic factors. Everything can be broken down to that. So if you've got a linear factor, then we know that when we pull that fraction apart, there must have been one fraction that had something over that linear factor. That must be there. If you have multiple linear factors, so x minus a to the power of n, then you write down one fraction for each of the powers. Now, we don't tend to go much past the square, but I mean, if it was cubed, then you'd have 3 of them, power of 4, you'd have 4 of them, and so on. The only other possible thing is we end up with a quadratic that can't be factorised. And in that case, on the top we write a linear function, the degree 1 less than the quadratic. So that's the idea. So let's look at a few. X squared on x plus 1. Well, we can do a polynomial division here because the degree on the top is 2, degree on the bottom is 1. And if we don't see it, we can actually do our division. So let's do that. And we end up with, there we are, x minus 1 with a remainder of 1. So I know we can rewrite that one as x minus 1 plus 1 over x plus 1. Well, I don't really need to do anything else to this because I can integrate all of that. So we get half x squared minus x plus the log of x plus 1. 3 on x squared minus x. Well, I can't do a polynomial division on this. So I factorise the denominator to see what we've got. And I've got x times x minus 1. So what that means is I can break this fraction up and I should get 2 fractions, something over x minus 1. So our challenge now is to work out what is a and b. If I multiply out by the denominator, I create this equation. There's different ways of doing it. I'm going to do it by just using clever choice of numbers for x. So x equals 0 is a good one to pick because that'll make the b disappear and I get a straight away, it's negative 3. The next logical number to pick would be x equals 1 because that'll make the a disappear and then I get b equals 3. So I've got a and I've got b. I mean, another way you could do it is you could look at it and say, I want to equate the coefficients of each term. And if you look at the left-hand side, the only constant there would be negative a. And on the right-hand side, the constant is 3. So negative a must be 3. And if I look at the coefficients of x on the left-hand side, I would get a plus b. And on the right-hand side, there is no x term. So I know a plus b must equal 0. So I could have done it that way. Anyway, whichever way we did it, there's our integral now. And they're both log functions. So minus 3 log x plus 3 log x minus 1. But because the coefficients of the logs are the same in magnitude, I'm going to use my log laws and pull it all together. And we get 3 log x minus 1 over x. Again, I can't do a polynomial division here. So let's factorise the bottom. We got x minus 5, x plus 2. So it should have been able to split up into 2 fractions, something over the x minus 5, something over the x plus 2. Which one did I do first? Negative 2 or 5? They're logical ones to substitute in. I've gone the negative 2. That gets b equals minus 3/7. And when I do x equals 5, I get a equals 10/7. Again, you could have equated coefficients. You could have said a plus b is 1 because of the coefficients of x. And if you look at the constants, 2a minus 5b must be 5. In simultaneous equations, you could work out a and b. So this is what we end up with. And again, we end up with log situations. And if you think about it, we're expecting a lot of logs here. Because if you've got a linear function on the bottom and a constant on the top, well, that is our standard integral for a log. So it's not surprising we're getting all these logs. So I've got 10/7 of log x minus 5 minus 3/7 the log of x plus 2. I haven't bothered recombining them because the coefficients aren't the same. I suppose I could have made them the same, because I could have brought the 10 into the first one and made it to the power of 10. It would have had a 7th out the front. The second one, I could have brought the 3 and made it cubed. Then it would have had a 7th out at the front. I just don't bother with ones like that. Okay, dx on x cubed plus x. So here's one where we've got a quadratic that does not factorise. Therefore, my two fractions, well, there'll be an a over the x, but then a linear function over x squared plus 1. What did I do first? X equals 0. X equals 0 is good because it's going to get rid of the b and the c. So I end up with a equals 1. There's nothing stopping us subbing in imaginary numbers, because by subbing in I, now the a will disappear, because I squared is of course negative 1. So I end up with negative b plus c I equals 1. I equate the real and the imaginary. So the real part, b, must be negative 1. And the imaginary part is 0 because there is no imaginary part on the right hand side. So I've got a, b and c. So there is our integral. 1 over x, well that's going to be a log. And the second one again is a log function. It'll end up being minus a half the log of x squared plus 1. I didn't bother with the absolute value sign on that second one because x squared plus 1 is always going to be positive. Whoa, now we're getting interesting. I've got a repeated root, the x plus 1 squared, and I've got a quadratic that doesn't factorise. So I'm going to have 3 fractions here. I need one fraction for each of the powers. So I've got a on x plus 1, b on x plus 1 squared, and then the third one, a linear function over the quadratic. Whew, what can I pick to make things disappear? Well, negative 1 will make the a go away, and it will make the c and the d go away as well. So I get b is negative a half. Now what to do? Okay, let's do x equals I, because that'll make the b go away and it will make the a go away as well. C and d I can now work out because I equate real and imaginary parts. I get c is 0 and d is equal to half. I still need to find a. So now I'm just going to sub in an easy number. And 0 is always easy. If I sub in 0, I get 2a plus b plus d equals 0. We've worked out b and d. So now we can work out that actually a turns out to be 0 anyway. Therefore, there is my integration. Minus 1 on 2 x plus 1 squared plus 1 on 2 x squared plus 1. Finally, something that's not a log. That first one, du on u squared becomes minus 1 on u. And the second one's an inverse tan. So we end up with a half of 1 on x plus 1 plus the inverse tan of x. There is yet another way of finding these values. And this is reasonably popular. It's what's known as the cover-up method. Now, most people show you the cover-up method for linear factors. So let's have a look at it. You've got something like this. If you want to work out a, well, what you do is work out a is function a on a minus. Basically, you substitute whatever little a is, and that'll get your answer. Why is it called the cover-up method? Because have a look at the answer. It is the right-hand side. The only thing that's missing is the factor of x minus a on the bottom. So the one that you're trying to find, you sort of cover up, and then just substitute into everything else. And then to do b, same idea. I cover up the x minus b and substitute b into everything else. To find c, I'll cover up the x minus c and substitute c into everything else. I hope you appreciate why we have to cover it up, because of course if I was to substitute c in, I'd get c minus c, which of course is 0, and you can't have 0 on the bottom of a fraction. Okay, and you keep going until you found them all. So let's go back to the ones that we've already worked out. So it's really quick when they are just linear factors, because we look at this one and we say, I want to work out a. I'll cover up the x and I'm substituting in 0 because it was x minus 0. In other words, whatever makes the denominator equal to 0. Sub in 0, I get 3 over negative 1. It's negative 3. B, cover up the x minus 1. Well, 1 would make that equal to 0. You get 3 over 1. So b is 3. So really quick. for linear factors. So let's have a look at this one. Same idea. I want to work out the A, cover it up, substitute in 5, I get 10/7. Want to work out B, cover it up, substitute in -2, and we get -3/7. There's our answers. And most people stop there, but I don't. It does still work with quadratic factors as well. You just got to use complex numbers and use exactly the same idea. So I want to work out A, cover it up. What makes the denominator equal to 0? Well, 0 does. Okay, I can work it out. And that's where people normally stop. But, same idea. What makes x squared plus 1 equal to 0? Well, I does. So cover it up, substitute in, and I get that bi plus c is 1 on I. So we're finding both the b and the c in one hit here. So if that's the case, b is -1, c is 0. The fourth one then, how would I do that? Well, the a, again, it's a linear factor, so that's easy to do. Cover it up, sub in the 1. All right, now for b and c. What would make 4x squared plus 1 equal to 0? I on 2 would. So substitute in I on 2. Now we play around with this fraction. Eventually we get 1 minus 3 on 2i, and so we know b is -3c equals 1. You see, it's important to have a range of options, because that's probably not the best way to find b and c. I mean, it works, but it's possibly more time consuming than simply substituting a number in and coming up with simultaneous equations, or however you want to come up with the answer. So, you know, sometimes you'll do it one way, sometimes you'll do it another, just what's going to work out the best. What about the one with multiple factors then? Just a little bit more work, tiny bit more. So we've got this one. Now, A, that's going to be simple enough to find. A equals -2. But now here's my problem. I've got x minus 1 and I've got x minus 1 squared. Well, which one am I going to find, the b or the c, when I sub in x equals 1? Thing is, it'll always work out the highest power. So I can use the cover-up method to find c. Sub that in and I get 3. C is 3. So how do I find b? Well, now I've got to use another method. So I'll just do a simple substitution. I'll let x equals 0, and we end up with b is 2. So having a range of options helps. What about this one then? Okay, well, I can find b. It's the higher power. I'll sub in -1. I've got the -1/2. I can find the c and d by substituting in I. So I've got the c and the d. Now I've got to find the a. All right, I'll let x equals 0. I end up with a plus b plus d is equal to 0. A ends up being 0. What about the one where the quadratic denominator couldn't be factorised? So this one. Again, the a, easy enough to find. Sub in -1, we get 1. Wow, how are we going to find the b and c? Remember, substitute in what would make it equal to 0. What makes x squared plus 4x plus 5 equal to 0? Well, all right, let's see. I'll just complete the square on that one. Oh, of course, we'll substitute in -2 plus I. All right, let's sub it in. Eventually we get there. B is -1, C is -3. Again, I'm not suggesting you would do that one this way, but what I'm showing you is the idea which most people just look at for linear factors. You can use it for others as well. It's just how much work's going to be involved in some of those higher powers and things like that. So 4D, we shall play with the partial fractions.